Our last speaker of this evening is Stella Kapodistria. She's an assistant professor at the Technical University of Eindhoven, and she is also working on networks and stochastic operations research problems. She has been recently setting up a research program on resilience engineering as part of a joint initiative of the 4 technical universities in the Netherlands about high-tech for a sustainable future. She has worked most recently on energy networks, and she's going to tell us about a very important question, predicting failures in a network even before they happen.
Thank you very much, Frank, for the very nice introduction. Before I start with the talk, I would like to ask the audience one question. Who drives a car? Can you please raise your hand? Okay. Would you change the oils in your car on some regular basis, or would you let them break? Those who agree to change the oils, please raise your hand. Okay. What would happen to your car if you wouldn't change the oils? Would the oils have a problem, or would the engine have a problem? So from the whispers I heard, I think that we all agree that the problem is not with the oil itself, it's with the engine. So the oil is just a mean for lubrication for the engine. And if it so happens that we do not change on a regular basis the oils of the car, then at some point the engine is going to break, and therefore the car is going to be useless. So when it comes to failures, sometimes we are interested not so much on the cause, but on the effect and the severity of that effect. So in the context of wind turbines and wind farms, I'm going to explain to you why it is so important to prevent failures before they happen. So in general, this is what could happen if we let a failure propagate. And typically in a wind turbine, a failure might start as a small, tiny crack on the blades. And then after several months, even in the process of years, that will propagate to the gearbox, that will propagate to the generator, and at some point that will propagate in the form of the explosion that you see here. So using data, I'm going to demonstrate to you how we can predict these failures in their genesis before they happen, understand the mechanism behind just by understanding the data behind it, and then I'm going to start with one single turbine, and I'm going to extend that to a wind farm, and then I'm going to extend this notion to an entire grid. So the objective of the talk is in some sense separated into 3 major questions. In the first part, I'm going to address how do we prevent failures when we're just looking in isolation in one single wind turbine. Then I'm going to extend this question into part 2, into how can we schedule offshore maintenance. So we have an entire wind park, and then in that wind park we want to prevent failures from occurring. And you will see that the nature maintains some characteristics, but it also has some endogenous differences. And then in part 3 I'm going to move towards to grids, and how can we make grids much more reliable. So starting with the first part on how do we prevent failures, I'm going to start with the data, because everything in this setting starts with the data. So every single wind turbine is purchased with already several sensors, and many service providers, they can actually give real-time access to what is the status of a wind turbine. And typically that comes with 3 color characterizations. Green, everything is perfect, clear skies. Orange, I see some warning behaviors. And then there is the red, things are starting to fail. And what I'm interested in, and this is part of the research that I'm involved, is actually determining which of the 3 stages we are. And for that purpose, what we do is we look at the data. One of the most important characteristics of the data that I'm going to demonstrate the algorithm around is based on vibration data. So vibration data, they work exactly in the same way as in seismology. So the only thing that is measured is displacement over time. So what you see here in the 4 blocks is, here you see vibration readings for the gearbox, here you see vibration readings for the generator, in one end of the drive, in the other end of the drive, again the generator, and here you see vibrations on the shaft. Typically when installing such a sensor that collects the data, it comes with an ISO standard. And the ISO standard says that upon calibration, if your vibration readings are between 0 and 1.06, and the 1.6 is exactly this orange line here of the warning, then things are good. If you're in the region 1.06 to 2.12, then things are getting out of control. And if you're in the region above the 2.12, things have gone completely out of control, and therefore you need to stop the wind turbine. And the first question that I had when I looked at that data is, and how much was the wind at that stage? Because I could imagine that the strongest the wind, the more increased the vibrations. So how do we take that into account? And the answer that I got is that we don't take that into account. All of this has been created in a laboratory in more or less a vacuum. But wind turbines, in practice, they're not in vacuum. They're out in the world, they are exposed to elements, and therefore this needs to be accounted. So this is exactly the same thing as someone telling you, you need to change the oils in your car every 5,000 kilometers. And then one could argue, but I don't drive my car so severely, so I would like to postpone that for 1,000 kilometers, or this particular type of oil actually permits me to postpone the change for a few more kilometers. So how can I make this personalized, and how can I also take the cost into account? Because preventive maintenance is nothing else than the terminology, the scientific in some sense terminology, or the everyday lingo for avoiding failures. It has a different meaning if I'm talking about my car, if I'm talking about my bike, and if I'm talking about a nuclear factory. So depending on the severity of the outcome, I would like to be, let's say, in some situations more modest, in some other situations less modest. So the first thing that we did was we looked at all the available data. And for a wind turbine, all the available data comes in the form of vibration readings for all the components, and you see here already all the components being sketched. Also temperatures for all the components, and in addition to that, information about the environment. For example, what was the ambient temperature, what was the wind direction, what was the wind speed, what was the humidity at that time. In addition to that, was the wind turbine operating or not? Was it connected to the grid? Was it not connected to the grid? Was it being maintained? What sort of problems did it have? So based on all that data, the objective that we had was to determine what would be a good strategy for preventive maintenance. And for that, we wanted to be able to do monitoring, we wanted to be able to do prognostics and to do forecast, and we wanted to be able to do diagnostics, identify back what is the component which is suffering, because that is also an important factor. And based on all this information, suggest condition-based maintenance, which means nothing else than the following. If the condition of the equipment has deteriorated, this is the point that you want to do maintenance. If the condition of the equipment is still perfect, then no one would like to do maintenance. So taking that into account, the objective that we had was identify the condition of the component. So the first thing that we did was we looked at the data of the generator. This is a generator which, what happened was, just before December 2014, it exploded. So the picture that I used in the beginning was not the picture for that particular wind turbine, but just to give you a level of understanding of what happened. While no one had predicted the explosion of the generator, they had already predicted that things were going completely out of control, and the problem lied in the generator. In practice, already here in November 2013, there was the first big disassembly of the generator. They disassembled the generator, they investigated what was happening, they were not able to figure out what was the problem. Then this happened again here in March 2014. And they let it run until December 2014. In some situations also the Wi-Fi was not working or some sensor was not connected, therefore we don't have data. And we also know that this is the ISO standard, which is set at 1.06, saying that if I exceed this value, then things are going out of control. And if I exceed the value 2.12, then things have gone completely bad and I should stop the generator. But this is the same exact as the oils. People give you a number, and then you want to personalize that number. And the operator of that wind turbine was also thinking that perhaps this is a hasty decision. We already disassembled the generator twice, so why should we go now into the process of repairing or even replacing a component which is so expensive. So after it exploded, what they wanted to discover is, could we have actually seen that? And then we were there to answer that question with mathematics. The first thing that we noticed is the following, that over time, as you see, what happens is that the vibration readings, they increase. So up until this stage that I have pointed with a green arrow, then the maximum vibration readings was between 1 and 2. After this stage, you see that they have gone above that level of 2. So I'm marking this with these 2 purple lines. So in a certain period of time, June until beginning of October, then things seem to be in control. So we use that as the baseline. And within that baseline, what we did was we created a model that actually predicts what should be the vibration. It discounts for what is the wind, because the strongest the wind, then the highest the vibration should be. It also takes into account what is the temperature, because this type of particular failure mode needs to have also increased temperature. So after taking into account all these things, what we did was predict what should be the level of vibration. And then we did a simple subtraction. What was the vibration that we were predicting minus the data that we were getting? And that actually leads to the figure that you see here. So if the difference is high, it means that the data is much more than what we had predicted. If the difference is very low, negative, it means that the data was actually producing less vibrations than what we had predicted. And those are 2 sides of things going wrong. So in that side, the thing that goes wrong is that the sensors are not well calibrated, which was another thing. Humans are calibrating the sensors in the same way that I check how good is the air in my tire. I feel it a little bit, it's a rule of thumb, and then I'm hoping that I'm right. But in practice, things can go awfully wrong there. So we can use the negative side as an indication that the calibration did not happen correctly. And I did not mark it with an arrow, but at that stage what happened was that the sensors, they were replaced. And therefore they had a different calibration method. There is also all this part here that you see marked in red, which indicates that the vibrations are much higher than the circumstances would have them. Therefore, there is something that goes wrong. And all that part is now, all the reds, you see them here. That indicates that it's not just everything that exceeds 2.0, 2.12, but everything in red. So I only personally saw a sea of red, which indicated that things have gone wrong, actually already from September 2013. Talking with the field service engineer that actually did the disassemble of the first generator here in November, just before November 2013, his perception on the matter was that, yes, I could see, I could feel it, but there was nothing to substantiate. So the data was indeed substantiating that. So one thing that we did was we developed different algorithmic approaches that actually predict when things are going to go out of control. So that was about the monitoring, and it was about the diagnostic aspect. Going then to the preventive maintenance, because nothing in the previous picture was accounting for a very important factor, the cost. So depending on the component, there is a different cost. Many operators of equipment, what they do in their maintenance strategy when they're not sure about which component has gone bad in some sense, is they just replace the cheapest one, because that comes with very low cost. So in practice, every maintenance, every failure aspect comes with a cost. So this is a very simplistic schematic ranking of the cost. If we just go and replace equipment without knowing what is the condition of the equipment, this is the most costly. If we just let the equipment fail and then we replace it after the failure, this is catastrophic breakdown, and this is the second most costly. The third is if I get from the equipment operator a phone call indicating there's something wrong here. So could you come and check it? Could you come and preventively replace it? So that comes already with a lesser cost. But what can significantly reduce the cost of operation is preventive maintenance. And the most simplistic framework of preventive maintenance is a planned maintenance. And for the wind turbine setting, the notion of planned maintenance is a maintenance that takes place every 6 months. So every 6 months, the field service engineer takes a huge handbook which describes every component of the wind turbine and every step of the process that the field service engineer needs to perform. He goes up on the wind turbine and then checks component per component and preventively replaces everything that he feels is going out of control. And that already can bring down the costs almost to half, and of course it depends on the context of the application, than just letting it break down. So in this context of the wind turbines, we wanted to understand what would be a good rule of thumb for such a wind turbine. So for every component that consists of materials which are metallic, for example, there is the notion of stress, there is a notion of load. So in the beginning of its lifetime, the stress that the machinery can tolerate is quite high. As time progresses, the stress actually that the machinery, the equipment can tolerate goes down. And when it reaches its stress limit, actually it breaks. So if I go back to my generator exploding, the whole process started from the blades. It was a small crack in the blades that propagated. So it starts typically with a material, and the material degrades over time. So then the question is, if I, from the data, can retrieve that, then depending on the cost structure that I have and depending on the action, and the third part is depending on this degradation mechanism, can I suggest a preventive maintenance strategy? And the answer is yes. There is a rule of thumb which we can actually prove mathematically that if I reach this threshold that you see here depicted with a green line, which depends on the cost structure, which depends on the time availability of the equipment, because not having a wind turbine operating, it means that we don't have revenue from that. So that also should be accounted as a cost, either because there was a breakdown or because we needed to preventively shut it down for maintenance. And also taking into account the failure probability between the planned scheduled maintenances, then we can derive this threshold, which is based on the condition. And on that threshold, we do condition-based maintenance. So with purple here, you see the periods in which we're doing the planned maintenance. So you can imagine this time between two planned maintenance to be nothing else than a semester. So every semester, there is the planned maintenance, and the field service engineer goes to the wind turbine. Already by looking at the data, we have an understanding, and we can say to the field service engineer that the condition we see it here, it's going to be below the level that we put our tolerance at, therefore you need to preventively replace it. Once such a preventive replacement happens, then after with some delay because it took some time for it to be repaired or replaced, then the equipment starts again with a perfect condition and it degrades over time. And this is repeated. So this is the most simplistic notion of preventive planned maintenance that a person can do on a single wind turbine. So now the question arises, how can we extend that to a setting of a farm? So we have a wind park, and in particular we're interested in an offshore wind park. And the reason behind offshore wind parks is that they are difficult to access. For an offshore park, someone needs to hire a boat, someone needs to hire the expert engineer. The conditions weather-wise need to be perfect, and only then things can be arranged. So we cannot say that today I know this based on my data and the monitoring that I have in place that the situation is going out of control, therefore let's organize the boat, let's organize the engineer, let's go to the sea and then let's repair things. So things need to be planned, and need to be planned months in advance. So the question now is, do we treat an entire wind farm offshore the same way that we would treat one single wind turbine? And the answer is sort of. So let me start with the particular schematics of this wind farm that I'm going to talk about. This is a wind farm offshore outside of, between, I think it's outside of Zeeland, and it consists of 60 wind turbines. And what we wanted to see is, are they all similar? Are they all identical? We know that they were purchased exactly the same year, they're exactly of the same type. But what I also understand is the following. If the wind is the most severe aspect when it comes to degradation of the material, then I would expect that the ones that they are on the exterior part, they suffer the most, while the ones that they are in the interior part, so somewhere here in the center, they would suffer the least. So what we did was we created a heat plot that indicates the load that those wind turbines actually have to tolerate in a period of 1 month. So what happens is that on average, the ones that they are here on the left side, they are the ones that they carry the most load, and that has to do with the average wind. So on average, the wind comes from that side, and the reason behind it is that Amsterdam is somewhere here. So basically there is land here, while there is open shore on that side. So the majority of the wind and the most intense gasps of wind, they do come from this side. So then the next question that we had is, if I choose a wind turbine somewhere here and I choose a wind turbine somewhere there, are they similar still? We know that they're made of the same material, they are of the same type, but now since I know that their load is different in a period of 1 month, would that change their behavior? So what we did was we consider a slice. So we consider a slice in the orange part here that you see that has not suffered much during that 1 month period. And we computed what is the probability that a wind turbine in that slice is going to fail in the next period of 6 months. And that probability is just a number p, very, very small, almost close to 0. Then we computed the exact same thing for that slice. And those two probabilities, they were not different. So that led us to the conclusion that the probability of failure in a period of 1 month is almost the same for all the wind turbines. And that gave us an idea. And the idea was the following. We are going to consider what is called opportunistic maintenance. In opportunistic maintenance, what happens is the following. If a wind turbine fails, then that creates the opportunity to also check the other wind turbines in the park. So we have the planned maintenance that takes place every 6 months, and we also have these unscheduled opportunities when one turbine in the park fails, or there is a problem. And what we did was we used that probability P, and we used the fact that those wind turbines are indistinguishable in the park to actually now just make a minor change in the figure that you saw before. So this was time, this is the stress. We start with a perfect condition, it deteriorates over time, but now we don't only have the purple instances, which are the 6 months, but we also have the blue ones. And the blue ones are nothing else than the moments in which something happened to one of the wind turbines in the park, and therefore a field service engineer needs to be on the spot. We model those instances by using nothing else than the probability of failure and the number of wind turbines. And then we know that these instances, they will become more frequent if I have more wind turbines or if the probability increases. And then that also changes a little bit the behavior that we have in terms of the preventive maintenance. Before we had one straight line that was indicating when we should do preventive maintenance. Now that is no longer a straight line. Now this has a periodic behavior, and the period is defined between a semester. So here you see the same pattern of period replicating the same pattern. And again, if we cross that threshold and we are below, this is the point in time where we need to do preventive maintenance. So this is the moment where we do preventive maintenance. And of course, this point here is exactly the same as the point as I had before. What changes is what happens in the opportunities. Because in the opportunities, I know that there's going to be some time still remaining until the scheduled planned maintenance. And then if my component is below this stage here, then I should already do opportunistic maintenance. So when I go from the one single wind turbine to the wind park, then that maintains the existing structures, but we can also take it one step up by increasing the available maintenance types and reducing the cost for that reason. And then the next question, which I'm going to address in the remaining 3 minutes, is how does that affect the grids? The introduction of sustainable energy, not only in the form of wind energy, but also in the form of solar energy, created a lot of uncertainty. Up until now, all the mathematical models, when it came to grid reliability, they were assuming that power, energy, is produced in a constant over time way. However, when I'm talking about anything that has to do with the uncertainty of the sun or the uncertainty of the wind, then we need to extend our mathematical understanding towards something more random. And what we noticed is that small failures nowadays, they have the tendency to propagate much faster, cascading over the network, and they don't do that. That was one realization that we had. They don't do that by propagating to the nearest link, but they propagate going to the weakest link. So it could be the case that this is the weakest link, so that would be the one that's going to be cut off. And this propagation of how the failure will occur in such an energy network has led to this picture, which was constructed by Deloitte in 2015. They tried to schematically depict what is happening in terms of power outages in the world. So what you see in the x-axis is time. So it starts in 1965, it goes all the way to 2015, and here you see the duration of the power outage in terms of hours. So if you say 1965, it might be because we were under-reporting things, or it might be because there were actually not so many power outages. If we look in the Netherlands, then between 1984 and 2015, there were in total 8 power outages. From 2015 to 2018, there are on average 6 power outages per year. And the reason behind it is that energy networks, they are actually aging, and they are aging disproportionately to how technology grows. And the other thing is that sustainable energies, they're in some sense training out the potential of such networks. And just to give you some very recent hints of what happened, so in April 30 of 2018, 6,000 passengers had to remain to the Amsterdam airport and depart with their flights the next day. And then in February 19 of 2018, there were power cuts that hit more than 75,000 homes in the generic northern Netherlands area. So in general, what we notice is that there is an increasing pattern in such power outages. And then the question is, how can we address this in a mathematical context? Without going into any details, the generic structure of such an optimization problem would be that I want to reduce the cost, I want to reduce unavailability because I want to have power grid available at all instances of the day of time, and of course I want to have the maximum reliability possible, subject to balance constraints, subject to the power flow equations with a level of randomness accounting for sustainable energies, and also satisfying failure limits. If we solve that, then we discover that the policy that the Netherlands have for the N-1 rule, which means that if one line in my grid fails, we can deal with it, but if 2 lines in the grid fail, then the entire network connected to that fails, is already indicating that this rule can be easily put in jeopardy. So with that sort of negative message, I would like to complete the talk saying that networks and algorithmics, they have the capacity to produce very fast algorithms that they can actually increase the reliability of such grids, of such constructions of networks, taking into account all the randomness and ensuring that the design is improved, the network is much more robust, and avoiding situations in the future where people are stranded in some airport or you're at home unable to see anything in the middle of the night. Thank you very much.
So thank you, Stella. So certainly the next time